Welcome to the screencast on limiting reactants. Now, what is a limiting reactant? In a chemical reaction, it's a substance that is used up first. It's the reactant, hence the name. It's on the left side of the equation. It stops the reaction. It's also the substance that limits the amount of product that can form, hence limiting reactant. Now, you already know a lot about this just in everyday life. For example, in a table setting, there's one plate, one fork, one knife, and one spoon. How many table settings are possible with 5 plates, 6 forks, 4 spoons, and 7 knives? And out of those items, which one is a limiting item? You can probably already figure this out by now, especially if you've ever set a table before. And that is that you can make 4 table settings. Now, why 4 and not 5, 6, or 7? It's 4 specifically because you run out of spoons. You have 4 spoons, and those get exhausted in the 4 table settings. You can't make a 5th one because you don't have a 5th spoon. So in this case, the spoon is the limiting item. It's not plates, forks, or knives. It doesn't matter if you have more plates, more forks, or more knives added into the mix. You're still only going to have 4 table settings because the number of spoons that you have limits the amount of table settings that you can make. So in this case, it's very much the limiting item. Now, the idea of limiting reactants applies really smoothly here in chemistry, particularly with stoichiometry and roadmap problems. And here's a case in point. When 4 moles of hydrogen are mixed with 2 moles of chlorine, how many moles of HCl can form? Here's a balanced equation. H2 plus Cl2 makes 2 HCl's. We're starting off with 4 moles of hydrogen, 2 moles of chlorine. We don't know how many moles of product we're having. This is pretty much a roadmap problem. The difference is that we actually have 2 reactant amounts now instead of just 1 reactant amount. So we've got this amount right up here from the H2 right here, and then we've got this amount of chlorine. In the past you've only gotten 1 amount, but now you have 2. So the way to do this is that you calculate the moles of product from each reactant, H2 and Cl2. Imagine that you've got all the chlorine in the world. If you only have 4 moles of hydrogen, how many moles of product can you make? And then you do the same thing again with the chlorine there. Imagine that you only have the 2 moles of chlorine, all the hydrogen in the world. Hypothetically, how much, in this case, how many moles of product can you make from the 2 moles of chlorine? And the limiting reactant is the one that produces the lesser amount of product. Whichever one gives you the smaller amount of product is going to be the limiting reactant, and the amount of product that you can make from that will be the actual amount of product that's formed. Here's a nice little flowchart that illustrates all this. So you start off with your grams of each reactant, convert each one to moles, then from that do a mole ratio to convert to the moles of product. With a smaller mole of product, or the lesser moles of product, will then be the actual amount of product that you make, and from that, if you wanted to convert it into grams or liters or particles, you can do that via roadmap calculations. And the key here is that the limiting reactant will produce that smaller amount. So here's a nice little conversion. To figure out the amount of product from hydrogen, you're starting with 4 moles of hydrogen. It's a 2-to-1 ratio based on the balanced equation, so you're going to make 8 moles of HCl. If you're starting then with the 2 moles of chlorine, do the same thing. It's a mole ratio, but it's in this case it happens to be the same ratio, 2 to 1. And you're only going to make 4 moles of product using the chlorine. Therefore, the 4 moles right here is less than the 8 moles of HCl, so that tells us that the chlorine right here is indeed the limiting reactant because it's used up first. And the actual amount of product that you're going to generate is the smaller number of the two here, is the 4 moles of HCl. This top number right there, 8 moles of HCl, is completely useless other than to determine how many moles of product you get. The lesser amount right here is the actual amount, so this number right there, you're never going to use that in a subsequent step. Now, how much H2 is left unreacted? To figure this out, this is a common follow-up problem to limiting reactants. You're usually asked, what is the limiting reactant, how much product can you make, and how much reactant do you have left over? Well, the hydrogen is going to be left over because the nitrogen there was going to be, I'm sorry, not the nitrogen, but the chlorine here is all used up. And that's another feature of limiting reactants is that they're completely exhausted or used up in a chemical reaction. So how much hydrogen is left unreacted? You would solve for how much hydrogen is first used up in a reaction and then subtract that amount from the initial amount. So since I know that I'm making 4 moles of HCl based on this calculation right here in the previous slide, I do a mole ratio to figure out how many moles of hydrogen it takes to make that. Well, it must take 2 moles of H2 to make that, and that's just from the mole ratio. Now, since we used up 2 moles of H2 and we started with 4 moles, how much do you have left over? Just 4 minus 2 is 2. You're going to have 2 moles of H2 in excess. And I always label that as in excess. It's not to be confused with the awesome 80s rock band in excess. You should check them out if you haven't ever done that before. But 2 moles of H2 in excess is how much you've got left over. I would strongly suggest that when you do this problem, you label these steps. How much do you have initially? How much did you just use up, which you just calculated from this step right here? And then how much do you have in excess? Here's a sample problem. If you have 4.8 moles of calcium mixing with 2 moles of nitrogen in the following reaction, here are the classic 3 questions. Identify the limiting reactant. Is it calcium or nitrogen? How many moles of product are actually going to form? And then how many moles of your excess reactant remain? Try to do this on your own based on the previous problem that we just went through. You can go back a little bit and take a look at that this little flow chart right here. Follow through with this and see if you can come up with the actual number. Pause the screencast if you need to, and then we'll go through the steps in just a moment. Here's how to do it. You would first start off with your moles of reactant. 4.8 moles of calcium. How much product can I make from that? 3-to-1 ratio from the balanced equation. 1.6 moles of product. How many moles of product can I make from nitrogen? If I start with 2 moles of nitrogen, which is given to me in the problem, it's a 1-to-1 ratio, so I'm going to make 2 moles of product. 1.6 is less than 2.0, so that tells me a couple things. Number one, tells me that this will be the actual amount of product that I make, 1.60 moles, and it also tells me that whatever made this is my limiting reactant. In this case, it's the calcium. Calcium must be limiting. Notice here that I have almost 3 times the amount of calcium as I do nitrogen right there. Actually, it's a little more than 2 times as much. In any case, the number of moles that you have right here that you start with, the 4.8 and the 2.0, never use those as indicators for limiting reactants. Those don't take the mole ratios into account. So these numbers are not any sort of predictor for which reactant in this case will be limiting. So all the calcium is used up because by definition all limiting reactants are used up. You're going to generate 1.6 moles of product. We got that from right there. And calcium, of course, has to be the limiting reactant because it makes less product than nitrogen technically can. Now, how much excess reactant do you have? Well, the nitrogen has to be in excess because calcium is limiting and it's all used up. I started off with 1.60 moles of product. This is the number that I got from right here, from that previous step. So I start with that. I figure out how many moles of nitrogen it takes to make that. It turns out the exact amount. It's a 1-to-1 ratio. This, of course, comes from the balanced equation right there, 1-to-1. So I had to use up 1.6 moles of nitrogen. To make that. So if I've got 2 moles of nitrogen initially, and I've used up 1.60 moles of nitrogen, the amount left over must be the amount that's in excess, which in this case is 0.40 moles of nitrogen. Now, pretty much these are the basics of doing limiting reactant problems. You can dress them up a little bit by instead of starting with moles, you can, in some cases, start with grams. And these problems are more or less a very typical type of limiting reactant problem. It's just like a roadmap problem where, in this case, you have 2 numbers that are starting as masses, convert them into moles, and then just do the steps that we've been doing moments ago. So this would be a good opportunity for you to pause the screencast. Again, do this problem, but the first thing that you should do is just convert those masses into moles and then just plow through it. So pause it, try it, and then restart it once you have an answer. Here we go. You've got 8 grams of hydrogen. I'm going to convert. We used very exact numbers here, 2.016 grams of H2, 1 mole. So now I've got mole numbers. There's my mole ratio. This is my mass of product. I'm going to be making water here. So hypothetically, I can make 71.5 grams of water if I use up all 8 grams of hydrogen. Oxygen, starting off with 24 grams divided by its molar mass. My molar ratio is 2-to-1 now. The molar mass of water, in this case, a very exact 18.02 over 1, which will give me 27.0 grams of water. This number is less than this number, which tells me 2 things. It tells me that this is the actual amount of water that I'll make, 27.0 grams. That's my actual